Hello, thank you for coming. So this is a joint work with Eric from Gothenburg. We've been working in this problem for some time now. So today we'll explain what we are doing. I will start defining the model and explaining the problem. Then I will show some strategy on how we think, how we're gonna solve the problem, and then I will present a sketch if time allows. So the problem is quite simple. We pick basically, well, it's quite simple to explain, but very difficult to put it into very formal mathematics, but I'll be very short here. So we define a post-1 point process on the space of line. This is the AD. And we put some marks on them. These marks should be interpreted as a time parameter. So as time goes, we will keep throwing some cylinders in the Euclidean space. And then afterwards, we project everything and are interested in all the cylinders. We forget all the marks and are interested on only the cylinders that arrived up to time t. Sorry, the lines. After choosing the lines, we just draw a cylinder of radius 1 around those lines. And then we consider the union of all the cylinders. Here's some illustration. So you just keep throwing some random cylinders in your, yes?
What's AD1?
AD1 is the space of lines in RD. Okay? So that is where you define your post-1 point process. So you pick one line according to a post-1 process. Okay, then we can define the cover time. So this is the smallest time such that some set is completely covered by your cylinders. So here, in this example, we take this red square, and then we check the first time that this is completely covered by your cylinders. We will be interested in studying this cover time when our set grows to infinity in some sense. So this is what we will be studying. Okay, so the first result that we get, more or less, if you do your calculations based on the Poissonian nature, is that the cover time of a single point is exponentially distributed. So we will do something that is completely wrong, but we will illustrate what I want to achieve. So if the cover time of each point were independent, and we define a very nice notion of limit, we could do these calculations and get to this kind of distribution here. So this double exponential, if you are familiar with extreme value theory, is known as the Gumbel distribution. And we believe this is the expected result that we want in this sense. But this is completely wrong, all right? So, because, well, you can see clearly that the cover time of a single point is not, they are not independent. If you have information on one point, you don't have in another, you have a lot of information on its neighbors. So, but, well, this is what we expect to get, and then we did a different thing. So the first problem is this independency here. And unfortunately, yes?
How does A come to the right side?
What?
Set A?
Yes?
On the right side?
Right side, where?
I mean, there's an expectation of, there's an exponential of e to the minus
T.
Yeah, but A is...
Yeah. A should disappear with the limit. This is the problem. Don't it's just some... This is completely unreasonable, all right? It will become clear here. So this is one of the challenges of this kind of problem is what we get with what we call long range correlation. So the thing is, in the Euclidean space, if you have disjoint sets and you have information on a cylinder hitting one of those sets, then you might have information on the cylinder hitting the other set. And well, this is a problem because this usually makes the problem quite harder and but much more interesting than when you have a finite, compact or finite sets, when you try to cover this with finite sets. What happened is that in 2014, Dickinson and Winch, they published a paper and saw that this correlation, although it exists, it decays polynomially with the distance. So if the sets that we are trying to calculate these probabilities are very far away, so this correlation is very, very small. And fortunately, this is enough for us to get the result. So, and now I will discuss this strategy, or how we're going to try to tackle this problem. And we will consider two different cover times that I will define soon. So that are much more easier to work with than the cover time that we are trying to prove. One of them is the discrete cover time, and the other one will be the well cover time. They will be clear soon. And we'll have this inequality in this direction here. So the strategy, I think, could be clear here. So if you have a result for this guy and for this guy, we take some limit, and then we get to the result for the real cover time. Okay, so what are these cover times? The first thing that we need to define is the well-separated set. So we pick a parameter rho that is usually quite small, and we squeeze the maximum number of points inside the set that we want to calculate. So in this case here, I got the red ball is a ball of radius rho, and we can place 7 points inside the ball of radius rho, such that these points are at distance at least rho. So they are well separated in this sense. Then for the discrete cover time, we just ask for this, we call the set a superscript rho. All right, so this is the separated set regarding this, the red set, the set that we want to cover. Then the discrete cover time is the time that the minimum time that is needed to cover just this A row set. So we won't just cover the points. And then, as you can see, it's much easier to cover these points than to cover the whole set. So we have the inequality in the correct direction. For the well cover time, it's a little bit complicated, but well, hopefully the beautiful pictures that I made earlier will help you understand it. So we place a ball of radius rho centered in which one of these points. You'll get a picture like this with all these balls. And then we say that the green balls, they are well covered if they are contained in one cylinder. So in this example here, we have that these two balls, they are contained in this cylinder here. So these are well covered, and this ball here are contained in this cylinder. So this one is well covered. This ball is contained in the union of the cylinders. So although it is covered, it's not well covered. And then naturally we say that the red set is well covered if all the balls from that we will obtain from the A row set are well covered. So in this case, also you can see that although the red set is covered, it's not well covered because you only have these three balls well covered, not the other ones. So with these definitions, we can prove these two theorems here. One for this one for the discrete cover time, and this one for the well cover time. And then they differ by this parameter here. So if we fix a separation and then we take a sequence of increasing sets, there are some regularities that we should ask for the sets, but I don't want to go into details here. And we get just the difference between this. And then one might ask, okay, let's just take the limit when rho goes to 0, and then we get the equality, but this is not so simple. There are some problems when doing this, so. Good. So I have some time. I will go for the strategy of the proof. It's very simple. So I'll do this for the well cover time. So this was based on a proof by David Bilius in 2012, where he did something, some covers, but with a completely different setting. But the steps are the same. The difference is we have to do things again. So they are completely different. So the first step is solve the long-range correlation problem. That was, we used the result by Tikesum and Winched, and then we can show that if we have small and distant sets, they are covered almost independently. So basically, yeah, exactly this. So if you have a lot of points, like small islands as a set that you want to cover. So because of the polynomially decaying, they are covered almost independently. And by almost independently is that the dependency in some sense decays with the distance between the sets. So this is the first step. The second step, and this is not very difficult to prove, the second step is a little bit more complicated. But basically it says that if you take just before the set is covered, the picture that you are left is exactly the one described in the previous theorem. So you have these islands here, and then we can apply the first theorem. So this is a little bit difficult to explain, but there is a picture. So we have a red set somewhere here completely covered, and if you go back in time, just before the set is covered, a time epsilon before it, we'll have this small, very small sets, and then we can apply the previous theorem. So we roll some machinery here, and then we get this kind of theorem. So if you take a set large enough, we can have this big inequality here. And then here you can see the problem of taking rho equals to 0. There are some rho, you cannot just take rho going to 0 without considering the size of the set A going to 0. So basically, this proof works for those theorems that I showed before, but it doesn't prove anything for the real the real cover time and the cover time that we want to show. So some words for the discrete cover time. This is exactly the same. You just have to send, instead of covering a ball, you just cover a point, and you have the same. But you have to be careful to not just replace all rows to 0, because some of those rows, they represent actually the distance, the separation distance. Yeah, so these are the references I used in this presentation, and thanks for listening.